Hi everyone, thank you for being here today at this webinar on statistical modeling, which is illustrated with XLSTAT. My name is Jean-Paul Maalouf, many of you already know me. I'm a statistics consultant at XLSTAT, and I'll be very happy to talk to you today. I'll try, as usual, as much as possible to use intuitive terms and avoid mathematical formula. You may download the handouts of this webinar, so the presentation slides as well as the data we will use in the handouts section of the webinar platform. You can also ask questions anytime you want using the chatting window, and I'll try to answer them twice during the session, so once at the middle of the session and another time at the end. And don't use the raise your hand option. So if you want to ask a question, just choose the chatting window. And the recording of this webinar will be available starting from tomorrow. So you will receive a link to the recording tomorrow if you want to watch it all over again. Let's go. I'll start as usual with a small brief about XLSTAT that includes a historical overview. Then I will talk about my personal way of categorizing statistical tools into different families of tools. Then before switching to statistical modeling, I'll do a small reminder about statistical testing. Then within statistical modeling, I will start with the principles, and I will illustrate those principles using a very simple example. Then I will talk about simple linear regression. This will be our first complex model we will illustrate. And I will illustrate also ANOVA before talking about multiple linear regression. So I will do applications using XLSTAT and a real data example. Then I will talk about a guide that we developed here and that is available on the internet, and that will let you choose an appropriate modeling tool according to your data and your questions. At the end of the presentation, you have two appendices, one on the residuals, and that concerns alternative verification methods for the hypothesis on residuals. We'll see all of this later on. And another appendix on alternative modeling tools. So you'll be able to check them out if you want to take a step further. Who are we? XLSTAT is a user-friendly statistical add-on software for Microsoft Excel. I think most of you have already tried to use it, and those of you who haven't, you'll get an overview of the software today. XLSTAT is a growing software and has a growing team. The development phase started in 1993. The first sale occurred in 1996. In 2000, the Addinsoft company, which develops today the XLSTAT software, was created. In 2006, we had a new version with two types of coding languages. In 2009 and 2015, we developed new products that are related to specific fields. In 2016, we had two new major releases. First, the cloud version of XLSTAT that works on Excel 365. So that works on the cloud, basically on the internet. And it now includes around 12 or 13 features. We also released last year the XLSTAT free edition, which is an edition that includes a limited number of features, but that you can use without having any specific XLSTAT license. This year, we've introduced the R interface in XLSTAT. So from 2 weeks ago, you are able to implement your own R procedures within XLSTAT dialog boxes and use them from Excel and XLSTAT. In a few numbers, XLSTAT holds more than 200 statistical features stored in general or field-oriented solutions. We have more than 100,000 users around the world. We are 22 employees. We have more than 220 visits per month on the website. The software is available in 7 languages, and we have 10,000 downloads of the software every month. So here's my personal way of categorizing statistical methods into different families of methods. First of all, we have descriptive statistics that allow summarizing data using simple statistics or charts, and those data are usually univariate, or bivariate, or maximum with 3 variables, data with 3 variables. So the most common tools in this category are the mean, the standard deviation, box plots, scatter plots, and so on. So descriptive methods allow fishing for hypotheses. Then exploratory methods allow having the same kind of reasoning, but on wider data sets. So in descriptive statistics, we are describing small data, like small data set in terms of number of variables or columns. With exploratory statistics, we are able to generate hypotheses to fish for information in wider data sets. Then statistical tests allow to accept or reject very precise hypotheses, assuming error risks. So we've seen in the previous webinars that those approaches are very complementary. So description and exploration on one side and tests on the other. Here you fish for hypotheses, and here you test for hypotheses. Today, we are going to talk about statistical modeling that help us understand the way a variable evolves according to a set of other variables. So typically in modeling, we find regression, ANOVA, ANOVA, and many other methods. So you are able to find recordings of previous webinars on descriptive statistics, exploratory data analysis, and statistical tests by clicking on those buttons that are available on the PDF that you are able to download in the handouts section. Today we'll talk about modeling, and next week, on the 7th of December, there will be a webinar on ANOVA, because in the previous webinar season, there are many of you who asked for a specific webinar on ANOVA. So this will be for next week. I hope I'll be able to talk to you also next week. So click here to subscribe. The webinar is free. Here's a small reminder on statistical testing. Statistical tests allow to accept or reject a very precise hypothesis, assuming error risks. So this is what we've seen in the webinar 2 weeks ago. So we first start with a question whose answer is usually yes or no. Are averages A and B the same? Usually statistical tests imply 2 hypotheses that challenge each other. The null hypothesis that we also refer to as H0, and that you can write generally with an idea of equality, of equivalence. Usually H0 is written like this: average A equals average B. The alternative hypothesis implies an idea of a difference. So HA, average A is different from average B. Statistical tests compute a number called the p-value that is bounded between 0 and 1. And this number is very important as it allows us to take a decision regarding the rejection or not of the null hypothesis and the acceptation or not of the alternative hypothesis. So if the p-value is small enough, or if it's lower than a certain threshold we define specifically before running the experiment. So if the p-value is small enough or lower than a threshold alpha, we reject the null hypothesis and accept the alternative hypothesis, assuming a risk proportional to p-value of being wrong. So basically, if the p-value is very low, we reject the idea of equality and we accept the idea of a difference between the 2 averages. And we take a risk of being wrong that we assume. So it's very important to have this in mind for the following part. So now that we've finished with this small reminder, let's talk about statistical modeling that helped me understand the way variables evolve according to other variables. So here's a definition of statistical modeling, which is, I think, intuitive. A statistical model is a simplified representation of a phenomenon using numbers. It allows to better understand reality and to do predictions. So statistical models just help us approximate reality using simple numbers. Let me illustrate things with a very, very simple example. Somebody asks you, what is the height of French people or the size of French people? And this same person gives you data stored in an Excel file. There it is. So you have this table that contains height information of a representative sample of 200 French people. So if we got back to this question, I propose two ways of answering this question. The first way, which is, I think, quite unpleasant, you recite the whole table row after row. So can you imagine you are in a conference and you want to refer to the global height of French people, and you just take this data set and you recite all the numbers. Do you think the people who attend the conference will be able to grasp this idea of French people height? I don't think so. There's another way of answering the question. Instead of taking each number one by one, you compute the mean and the standard deviation over the 200 values and use these two numbers as an answer. So instead of giving the 200 numbers, you just provide the mean and the standard deviation and assume that the mean and the standard deviation are representative of the mean and the standard deviation of the whole population of French people. So of course you are losing some precision in providing these two numbers. So there's some information that you lose, some specific information on each and every French person that you lose. But what is gained on the other side is that you only need to have two numbers. You only have two numbers to have a global overview of French people height. So this is a way of modeling data. So representing French people height by a mean and a standard deviation is already a first way to model this height. So we are summarizing things using two very simple numbers. So if I get back to this definition, a statistical model is a simplified representation of a phenomenon using numbers. It allows to better understand reality or to have a better idea of reality or a more understandable idea of reality and to do predictions. Now technically, how does modeling work? A model allows to explain one or more dependent variables using one or several independent variables through mathematical equations that involve parameters. So we often have at least one dependent variable or one variable we are seeking to explain using one or several independent or explanatory variables that are here to explain this variable we want to explain. And the link between the variables we want to explain and the variables that are explanatory is simply an equation that involves parameters. So all of these, so variables, independent and dependent, parameters, and the mathematical equation, so all of this group is called a statistical model. Now the example of mean and standard deviation we just seen does not imply explanatory variables. We just have one variable, which is French people height, which is a dependent variable or a variable we want to explain. So this is a very, very simple model that does not imply explanatory variables. Let us take one case of a model which is a bit more complex, simple linear regression. I'll start with an example, of course. Then I'll talk about the principles. I'll do a demo on XLSTAT, and I'll run interpretations of the outputs before talking about the hypothesis on residuals. So let me tell you about the data set we're going to work on. So this famous data set, which is an online shoe selling platform, here I have clients, which are individuals and which are stored in rows. And those clients are described by different variables stored in columns. Some of these variables are qualitative, like origin and gender. And some of them are quantitative, like height, shoe size, weight, invoice amount. So here's our data set we're going to work on. There's a question I want to answer. How does invoice amount, which is this column, vary according to time spent on site, which is this column? So we'll use statistical modeling to answer this question. So first thing we can do when you have a question like this is try to see visually how those two variables relate to one another. So I remind you of a specific tool we've seen in the descriptive statistics webinar, which is the scatter plot. There it is. So here we have invoice amount on the y-axis and time spent on site on the x-axis. What can we see here? So when time spent on site increases, invoice amount decreases. There's a negative relationship between the two variables. So how can we model this relationship? How can we summarize this relationship? So one of the ways of summarizing this relationship is using a straight line. And this straight line is simply a model that we call simple linear regression. And the equation of a straight line like this can be written as such: y equals a multiplied by x plus b. So y is the data on the y-axis, and y is the y-axis, and x is the x-axis. And a and b are what we call parameters. A will be the slope, and b will be the intersection between the y-axis and the model or the line. Now, this is one of the many ways of representing something that decreases. We could have used another model that is more concave, like this. But I chose the linear regression just for convenience. How can we translate this in terms of variable names? I replaced here the y with the variable name invoice amount and the x with the time spent on site. So here's how my linear regression can be written as well. Invoice amount is my dependent variable. This is the variable I want to explain. Time spent on site is my independent variable or explanatory variable. And very often we represent the dependent variable on the y-axis and the independent variable or variables on the x-axis. Then this slope and this intercept, so this intersection between the y-axis and the model, are called the model parameters. So as I told you, a model is an equation that links dependent variables and explanatory variables with parameters. So this is our way to simplify reality, a straight line model. This is a way of answering the original question. So we can say that invoice amount linearly decreases with time spent on site. And of course, there's something a bit frustrating about this model. It's that it doesn't really capture all the variability in the data. So it doesn't really touch each and every blue dot, each and every data point. So there's some precision that is wasted somehow, just as the first example I showed you about the mean and the standard deviation. Always when you apply a model to a data set, you lose some information. But this information that is lost is compensated with the simplicity of interpretation of things. This information, those differences between the blue dots, so the data, and the model, are called the model errors or model residuals. So all of these distances my model was unable to capture are called the residuals. So we chose linear modeling or linear regression, but this was absolutely not mandatory. So there's no miracle model that you can choose and that always best fits your data, but you simply need to choose a model that is the most convenient to answer the question and that implies parameters whose interpretation is easy. Now let me tell you something funny. ANOVA may also be perceived as a statistical model. The only difference with regression is that the explanatory variables, so the variable on the x-axis, are qualitative. Here's an example. If you took the salary of our clients according to their origin, so clients from Earth, clients from Pluto, and clients from Mars. The origin is a qualitative explanatory variable, and thus we can apply an ANOVA model to think about salary. The white bubbles are the averages of each origin, and the blue dots are the data. Here's how the ANOVA model can be represented. Let me explain things further using the equation. The salary can be written as such. You take a reference level, such as Earth, plus the distance between this level and the averages of the other levels. So if I want to take the value of this average, I take the average of Earth and I add the difference between this average and the average of Earth. So here I have basically three parameters. I have one parameter for the reference level, which is Earth, and I have two parameters that correspond to the difference between the other levels and the reference level. So this is only to tell you that ANOVA can be perceived as a statistical model also. And of course, the model is not definitely precise, not 100% precise, because it doesn't really capture all the data points. So there are residuals. It doesn't capture all the data points, but it's quite convenient to understand a bit the salary of my different origins. So I take just the averages of each origin instead of taking each and every data point. So here, once again, the ANOVA model allowed me to understand in a simpler manner the mean salary according to origin. ANOVA, linear regression, and ANCOVA are all linear models. How do we estimate those parameters? Let me take the case of simple linear regression. So the best parameter values are those that minimize the residuals sum of square. So I won't talk a lot about this because it's not very important for the next steps. But for those of you who are interested by the mathematical aspect of things, here's how things are done. So the best model is the model that minimizes the distances between the dots and the model. So the best line is the one that minimizes those red arrows. And those red arrows are represented in squares here. So the data minus the model. And so the sum of these arrows, or of the squares of these arrows, should be minimized. This can be computed by solving the equation of the derivative of this value equals 0. This is what we call least squares estimation. Now, how can you apply simple linear regression using XLSTAT? Here's my data, which is stored inside Excel. And here's XLSTAT, which is an additional tab that gets installed inside Excel also. So XLSTAT includes many menus in which you can find several statistical methods that you can apply directly on your data in Excel. Linear regression can be found under the modeling data menu. There it is. So let me click on it, and here I have my linear regression dialog box that appears. And within this dialog box, you can select the data on which you want to apply your regression. So here my dependent variable is invoice amount. So I click here and I select my data like this. I can also select my data by clicking on the I header. And the explanatory variable I want to use is time spent on site. There it is. I click OK as soon as I'm ready. And here we go. The outputs appear in a new Excel spreadsheet automatically. And there are many interesting information that is displayed. But let us focus on this table, which is very important in statistical modeling, as it summarizes all the information on the estimation of parameters. So I will comment on this using my PowerPoint presentation. Here we go. So first of all, in this table you have several rows and you have one row per parameter. Intercept is B, so the constant in the equation, and time spent on site is the slope, it's A. So here the slope estimate, the least square estimate of the slope is negative. So we could have expected that because the relationship between time spent on site and invoice amount is negative. Then here you see very important p-values. Those p-values allow us to see if our parameters are significantly different from 0 or not. Each p-value is related to two hypotheses. A null hypothesis which states that the parameter equals 0, and an alternative hypothesis that states that the parameter is different from 0. So here the p-values are very low for each of the two parameters. This means that we can say with a lot of confidence that our two parameters are significantly different from 0. This means that this slope is significantly negative. And of course, we are doing estimations here, so we have confidence intervals around the estimation, so we don't have very precise and punctual estimations. Our estimations are uncertain, so we have confidence intervals around. Then an important also output here is the equation. So this is my y equals ax plus b with values of a and b that were replaced here. So this is b and this is a. And you can use this equation to predict the invoice amount according to new values of time spent on the website. If you have new clients who are using your website, you can more or less predict your invoice amount, their invoice amount, using this equation. Then there's another output that appears within your XLSTAT linear regression report, and which is this one. So this is the scatter plot which we've seen earlier, but with some additional elements. The black line is the regression model, and you have two envelopes around, one which is narrow here, the gray one which is narrow, and this is the confidence envelope of the model, of the confidence envelope which is related to the estimation of the parameters. You have another confidence interval or envelope, the full lines here, not the dashed ones. This envelope is wider, and this is the prediction envelope. And then there's a very important number here, which is quite famous, which is the R-square. It appears here in the report and also appears at another place. R-square reflects the goodness of fit of your model. And there's another kind of R-square which is called the adjusted R-square and which should be preferred. So the higher, the closer the points are to the model, or the closer the data are to the model, the higher the R-square will be, and the better the predictive quality of the model will be. Otherwise, the more your data are dispersed according to your model, the lower your R-square will be, and R-square is bounded between 0 and 1. Now, before really validating this model, now that we've estimated the parameters, before really believing in this model, we need to verify some assumptions about the residuals of this model. A linear model is only reliable under certain conditions that are linked to these residuals. So it's very important to check. But before telling you about that, I'll take the first set of questions you asked. What would a good value for R-squared be? I would say this depends on your question and your field of expertise. If your goal is to predict, you better have points that are very close to your model so that your upcoming predictions will be reliable. So you better have a very high R-squared. I won't give you any threshold because it really depends on your field of expertise. There are some people who in some fields who seek R-squareds of 0.99, others who seek R-squared that are higher than 0.9, people who seek 0.8. It really depends. But of course, if your goal is to do prediction, the higher the R-square, the better your model is. But if your goal is only to estimate the effects of different variables on an explanatory variables, then the R-square is not as important as in the first case. So if your goal is only to estimate these parameters and not to do predictions, then the R-square is important, but it's less important than if your goal was to predict. How can I visualize the points associated with the customers from different planets? I suppose you mean you want a line per planet. So this could be done using a typical kind of model that we call the ANOVA. Let me show you this guide. Maybe I'll show it to you right away and not at the end. I will show you a guide that lets you choose an appropriate modeling tool according to the question you're asking. Which statistical model should you choose? It's in our tutorials based on the web. Here you have a grid that allows you to choose an appropriate model according to the situation you have. So if you have quantitative data as dependent variables and you have qualitative variables as independent, you can run ANOVA. If you have quantitative data as dependent and quantitative as independent, we've seen that you can use linear regression. If you have a mixture of qualitative and quantitative variables as explanatory, you can use ANOVA. And this is related to your question, because what you are seeking here when you want to have one slope per origin, you are mixing two explanatory variables. Time spent on site, which is quantitative, and origin, which is qualitative. So you can run your ANOVA by clicking on modeling data. I'll do it quickly. ANOVA. Here, let me get back here. So invoice amount, and according to time spent on site. And here, notice the name of the dialog box that will switch now. As soon as I click on qualitative, here I get ANOVA. I will add the origin, and I will click on OK. And at the end of the report, I get one slope per origin. There are two that are very close to one another, the Earth and the Mars slopes, and the Pluto slope is quite far away. How is it that some models are almost identical with the prediction? Whenever I see these types of model, I suspect that there is something not quite right. Is it really possible to have a 0.99 R squared that is legitimate? Well, if you have many data points and few explanatory variables, then a high R square is legitimate and reflects a very good quality of prediction. Whereas if you have very few data points, if you have only 3 data points and you have 2 explanatory variables or 1 explanatory variable, then your R square will automatically be very high and it won't be really legitimate. Then do you really want to predict new observations based on a model which was built on only 3 data points? So I don't think it's a good idea. Why are my outputs always black and white? I think I know why. Because you have here in the XLSTAT options, you have different color settings you can play with. I think it's in the outputs. And here in the theme for, no, it's not here. In charts, yes. In the charts, you can select between modern, classic, and scientific. And if you have scientific, you will always have black and white. So you can switch to classic to have colors. Thank you for your questions. I will carry on now with the webinar. So now that we've built our linear regression, we'll check the assumptions about residuals. So a model is reliable, or the estimations of the parameters of our model is reliable only under certain conditions that are linked to residuals. And those are the main conditions we should check. First, residuals should be independent, no autocorrelation, and should have 1 measurement per individual or per statistical unit. So if you had 2 measurements for a specific client, here we would have had some autocorrelation between those 2 measurements as they're linked to the same person. So there shouldn't be any link between the measurements. They should all be independent. The population, or at least the population from which your residuals are extracted, should follow a normal distribution. Then you shouldn't have too many outliers or residuals that are too far away from the center. And residuals should have homogeneous variance. This is what you call homoscedasticity. Now there's a very simple way to check for all of these hypotheses. Let me show it to you. There's a very simple chart that allows you to diagnose this. You take your residuals versus explanatory variables chart that is available in your XLSTAT regression report at the bottom. So when you launch a regression on XLSTAT, you automatically get this chart. So you check it out, and if the residuals or the points are homogeneously spread all along this line, so the y equals 0 line, then your model is valid. And of course, the points should be more concentrated in the middle and more spread out the more you get far away from the center line. In our case, we can say that dots are homogeneously distributed around the line, so we can say that the model is reliable. There are other more precise ways of checking for those assumptions, and they are all in your appendix. So if you're interested, just check them out. You can run a normality test, for example, to check if your residuals are far away from, are significantly different from a normal distribution. So let me show you 2 common patterns of violations of the assumptions about residuals. First case, this one. This is a violation of the independence assumption. You see that the residuals are autocorrelated. When you see this typical periodic pattern with ups and downs like this is a typical case of autocorrelation. So this residual depends on this one and depends on this one. there's some kind of continuity here in the ups and downs. This means that the residuals are really depend on one another. And this often occurs when your explanatory variable is time and you have a periodic phenomenon that you are trying to model. So it frequently occurs in time series implying periodicity. Another case of violation is this one. When you violate the homoscedasticity assumption, here you have variance heterogeneity. So this typically appears in the form of a cone like this. One of the most commonly places where you find this kind of pattern is when you try to model some kind of a morphological trait according to age. Imagine you are modeling the human size according to their age. Well, babies have sizes that are not that variable, but the more you grow, the more your size could be variable. So this also is a violation of one of the assumptions. Parameter estimations will be wrong. Here are a couple of solutions when the assumptions are violated. Think about outliers. Do you have outliers? And is it worth it to eliminate them? Did you do a mistake while entering the values in your Excel spreadsheet? Or is the individual corresponding to an outlier really important in the population you are studying? So if that is not the case, maybe you could eliminate this individual and rerun your analysis. Then you can also transform your Y or your X data using transformations such as the log, the square root, or the Box-Cox transformation. And typically we transform the Y data and not the X data, but X data could be an option also. So sometimes this kind of transformations can make your residuals get closer to the assumptions. So you transform your data and you rerun your model and you check the assumptions on the residuals of the model built over the transformed data. You can also use a more convenient model. You can use a nonlinear model or a Poisson model. You can use also the Cochrane-Urquhart model when you have typical periodic autocorrelation. This feature is part of the XLSTAT forecast solution. So now that we've really talked about simple linear regression, we're going to add some other explanatory variables in our equation, and we're going to talk thus about multiple linear regression that could be written like this. So y equals a multiplied by x1, b multiplied by x2. X's are the explanatory variables, and each orange letter will be a parameter linked to each of these variables. So first, the goal. Multiple linear regression allows to investigate the linear influence of several explanatory variables on the dependent variable, and thus increasing predictive quality. But there are some warnings though. In addition to the assumptions about residuals, beware of overfitting and multicollinearity. What do I mean by those two things? So when you add explanatory variables, in the case of a multiple linear regression, you will increase your R-squared, but here's the warning, do not add too many of them. Why? Because if you add too many variables, and when your variables, the number of variables gets close to the number of observations or of individuals you have, you will have a model that will be too fitted to your data, a model that really passes through each and every data point. So if you add too many variables, the risk is to obtain models that are too fitted to your particular data and that will be consequently be less generalizable. So you will build a model that is super specific to a data set, and as soon as you want to predict a new observation, the prediction won't be very reliable because your model was overfitted over a small data set that you got at a certain point. Now, how can we control for this? You can use the AIC model quality index. that is a compromise between a good fitting to the data and a low number of parameters. So you can always compute an AIC index out of your model to see how good it fits your data, to see a compromise between model fit and number of parameters. So a good model, according to the AIC index, is a model that has a low number of parameters, but that fits well your data. But be careful, AIC is a relative quality index that should only be used to compare models with one another. The model with the lowest AIC is the best model in the model set. Of course, as I told you, there's no miracle model that is perfect for your data. Usually, you should maybe try different models that imply different sets of variables, and then compare those models, maybe using some criteria or some index like the AIC to select the best model in the set of models you are proposing. You cannot really interpret the AIC of one single model alone. The AIC is a relative index that should be used when you compare several models to one another. Second warning, beware of redundant variables. So some correlated explanatory variables may hide each other in terms of the effects on the dependent variable, or in terms of the estimation of their coefficients or parameters. This is what we called multicollinearity. And multicollinearity can be diagnosed using indices such as the VIF, which is the variance inflation factor. So some authors say that if the VIF linked to one of the explanatory variables is higher than 5, then this variable is super redundant with the other variables. Let me give you an example. When you are investigating in your work in environment science, and you are investigating the effects of day temperature and night temperature on some output, you may have multicollinearity because those two variables are likely to be very correlated. So there will be a competition between them in the estimation of their parameters. Also, when you want to model something and you include the weight and the height in the same model, weight and height are also likely to be very correlated. So it's not really worth it to include both of those two variables within the same model. You could have multicollinearity. Now let us do an application in XLSTAT. We will apply a multiple linear regression based on this question. Which variables among the height, shoe size, weight, and time spent on site have the strongest linear influence on invoice amount? And can we predict the invoice amount of 2 new clients? Here we go. You go to modeling data, linear regression once again. I will select invoice amount as a dependent variable, and I will select those 4 variables as independent. There's something important I want to check in the outputs. The multicollinearity statistics, which include the VIF. Just let me tell you that in the Options tab, in the Model Selection options, you can select the best model according to several criteria, such as the AIC. The best model, which is the model that implies the best combination of those 4 variables, according to these criteria. But I won't run this now. Here we go. Once again, I will focus on the parameter estimations, but first of all, you should know that XLSTAT provides you with all of these goodness of fit statistics, including the R-square, the AIC, and other statistics. So here's my model parameters table, on which I will comment using the PowerPoint presentation, but I forgot to check something very important, the multicollinearity statistics table. I apologize on this. There it is. Here you see that each variable is linked to 2 multicollinearity indices. So some people use the tolerance, others use the VIF. You can see that the height and the weight have super high VIFs. This means that height is redundant with the remaining of the variables, and weight is also redundant with the remaining of variables. This means that one of these two variables should be removed. Height and weight are super likely to be correlated, as I told you. So one of these two variables should be removed from the model before running it once again so that the estimations could be reliable. I propose to remove height and to run the model all over again. So I take linear regression, and here instead of taking those four variables, I'll take these three variables, and I click OK. And here my multicollinearity statistics are far better. So my VIFs are all lower than 5. So now my parameter estimations are more reliable. I will comment on them here. Here are my parameters and their least square estimations and associated p-values. So shoe size and time spent on site have negative influence on the invoice amount. But this negative influence is not significantly different from 0. So those parameters are insignificant. Besides, weight seems to have a very strong effect on the invoice amount because it's linked to a very low p-value. So we can say with a lot of confidence that this parameter is significantly different from 0 and it's positive. So as weight increases, invoice amount will increase. So last point we need to see in this question, it's about the predictions. Here in the data we have information relative to 2 new clients who haven't submitted any purchase on the website yet. We want to predict their invoice amount according to these data. So I will take my regression once again. I'll go to my prediction tab. I'll click on prediction, and here I will select the data I want to predict on. I remind you that in my model I have removed the height effect. So I take those data. I can also add observation labels, and I click OK. Here at the bottom of the report, you get your predictions. Carmen will probably pay $138 on the website and John $234. And of course, those are estimations, so you have confidence intervals around. Okay, so to conclude, I have already showed you this link to access the guide. Let's get back to this question about height. Somebody asks you what is the height of French people. There are different models that can help you answer the same question. Just to let you know that there are different ways of answering a question using statistical modeling. There is no miracle model. So height of French people is the dependent variable. You can first try to model this height using an average and a standard deviation. So this is called the normal distribution model. You can say that height depends on geographic origin. So in this case, you can use one-way ANOVA because geographic origin is a qualitative explanatory variable. You can say that height depends on age linearly. You can use simple linear regression as you have one quantitative explanatory variable. It depends linearly on age and origin. You have a mixture of green and red, so you can use ANOVA. It depends linearly on several independent quantitative variables, so you can use multiple linear regression, and you can also have several dependent qualitative variables. In this case, you can use two-way ANOVA, and on and on. So in summary, statistical modeling allows to investigate how dependent variables evolve according to explanatory variables using a mathematical equation that involves parameters. You can also predict using this equation. Linear models are reliable under certain assumptions related to residuals. And beware of problems related to the introduction of too many variables such as overfitting and multicollinearity. And according to variable types, different models are available. Check out our guide online. Thank you all for attending. All the features we've seen are available in all XLSTAT solutions except XLSTAT free. Let me take the last set of questions we have. What is the difference between linear regression and Pearson correlation if with both I get the same R square and p-value? Linear regression allows you to have an equation and has an idea of explaining something by something else. So you have a sort of a difference between the variable you put on the y-axis and the variable you put on the x-axis. The y variable is explained by the variable on the x-axis, whereas in the Pearson correlation, you are just investigating a relationship between two variables, and you can flip the chart, the scatter plot around and put the x variable on the y-axis and the y variable on the x-axis. So you don't really have this difference in concept between the two variables with Pearson correlation. What is meant by transforming data by using log? So this means transforming data using the logarithm. If I go back to my data set here, instead of modeling invoice amount, I can model the logarithm of invoice amount, which could produce residuals that get closer to the assumptions of linear models. So here I can calculate the logarithm of each number and use this column as dependent variable, not explanatory, dependent, sorry, to build my model. I have 10 dependent variables and want to test each dependent variable against one independent. Do I need to manually enter each test, or can XLSTAT run through each of the 10 dependent variables and display the results for each of the 10 model tests? Well, yes, you can do this automatically in XLSTAT. If you take your regression, if you take your linear regression like this, you can enter here many dependent variables and maybe one independent, or you can also take many. And when you click on OK, you will have one result per dependent variable. So you can do this automatically. How do you interpret a significant intercept? Well, in multiple linear regression, it rarely makes really any sense. Usually in multiple linear regression, you just focus on the parameters related to the slopes of the explanatory variables. The intercept is only here to adjust the equation and to make the equation good for prediction. How is multidimensional linear regression different from PCA regression? Well, PCA regression is a special case of regression that allows for multicollinearity. So you can run PCA regression with redundant variables. So this is one of the advantages of PCA regression over classical regression. Thank you all for attending. I hope you enjoyed the webinar, and I really love to see you all again in the ANOVA session next week. Have a nice day. Bye-bye.